Okay, welcome everybody to this promised recording to finish basically the discussion we started in class on some of the problems related to exam 4. So there were two problems because we ran out of time at the end where I just was giving you some ideas, but apparently we needed to discuss them further, and I promised to follow up with the recording. So here is a recording. So the first problem is the one that I think we did quickly, but we didn't really I didn't pay attention to the actual question, honestly. So this problem basically was asked, it will give you two disks, disk one. So it's not point particle, it's a disk. So we have to be careful in here. It's moment of inertia with respect to the center of mass, I with its own center of mass. So this center of mass depends, of course, on the system. So this one will be 1/2 of its mass times r squared. This one is m1, its radius is r1, and it's traveling with a velocity given to be 1.5 meters per second. And the other one, which is sitting, minding its own business, has a radius r2, which is 6 centimeters, and a mass m2, and they stick and they turn. So the first question, honestly, was asked about the angular momentum with respect to the center of mass, not with respect to the center of the second disk. So we have to be careful, and that's how we calculated it last time, and that's wrong. So let me answer the question correctly then. So we have two disks. One disk that is sitting 6 centimeters and another disk that is 4 centimeters. Last time when we calculated the center of mass, we calculated with respect to the bigger of the two disks. We really should have computed it. It doesn't matter, we found the same answer anyway. And once we find it with respect to one, we can find it with respect to the other one. Well, that's exactly what we did in class. So this distance is 4 centimeters. This is 6 centimeters. And we needed to find the center of mass, and we found it in here. So it was inside of the bigger of the two, because this one is 120 grams. This one is only 80 grams. So I'm going to start in here. So that's the origin. So the origin 0 is for the one where the 80 grams is. So that means the x of the center of mass, so that means the one that is sitting at 120 grams is sitting at 4 plus 6, which is 10 centimeters. So that gives me the center of mass from the center of the 80 grams is going to be equal to 0 times 80 grams plus 10 times 120 grams divided by the sum of the 80 and the 120. This is 0 because 0 times 80 is 0. This 0 cancels this 0 and this 0. And 10 times 12 is back to 120. Divided by 8 plus 12, that's 20. And that's 6 centimeters from this point. And that's exactly how we did. Last time we found it 4 centimeters from this one, which is 6 centimeters from the other one. So we needed the center of mass, but we really needed it from the smaller of the two disks. Now go back to our problem before they collide. So here is, let me draw this imaginary line just to help me basically visualize these two. So this one is traveling this way with velocity that is 1.5 meters per second before they collide and they stick to one another. And its distance from the center of mass, this point from here to here, is 6 centimeters. Right now, if I want to use the formula that we have done in lecture, R cross P, this is the R of interest times the sine of theta, because that's how the cross product works. So R, P, sine of theta. But R times sine of theta is the opposite to this R, to this angle theta. So as R is shrinking, theta is also changing in such a way the hypotenuse times the sine of the angle is equal to the adjacent, which is 6 centimeters. So this number is 6 times 10 to the negative 2 meters, r sine theta. So it doesn't change. I know we did this in lecture, but I'm just repeating it in here. So the angular momentum before, with respect to the center of mass of the whole system, which is in here, is equal to 6 times 10 to the negative 2 meters times the regular momentum, the linear momentum, which is the mass, which is 80 grams. Don't forget to convert it to kilograms, times the velocity, which is 1.5 meters per second. So that's this number. Of course, you're going to find it in the units of a kilogram. Meter and meter, that's meter squared divided by second. So that's the angular momentum before they collide. Now, I think there was some probably questions in here related to whether or not this collision is an inelastic collision. Immediately after they collide, they become they stick together. So this is a perfectly inelastic collision, as a matter of fact. So there is no conservation of energy in here in this system. Anyway, now the next question was, when they stick together, how much is the omega with respect to the center of mass, for rotation around the center of mass, basically. So again, when they stick to one another, the new angular momentum, so the L after, is the total I with respect to the center of mass, the combined center of mass. I don't mean in any of the two, times omega final. So we're supposed to find L. This angular momentum must be equal to the same number that we computed earlier. So we know what the initial angular momentum is with respect to the rotation around the center of mass. It is the same as the one after with respect to the same axis that passes by the center of mass, and equals to omega times this moment of inertia. So the whole problem then, in order to find omega f, which is just the number that we computed earlier, 6 times 10 to the negative 2 times 80 times 10 to the negative 3 times 1.5, and that is, of course, divided by 1.5, that is, I with respect to the combined center of mass. Okay, so I have two systems in here. So I, the whole combined with respect to the center of mass, to their common center of mass, is I1 plus I2. Okay, and I1 is equal to its own moment of inertia with respect to the center of mass plus its mass times its distance from the center of mass, from the axis of rotation squared. The distance between, let me explain this point in here. This is the parallel axis theorem, by the way. So its own moment of inertia with respect to its own center of mass is 1/2 mass times r squared. That's a disk. It's not a point particle. Plus, this is the distance from this axis of rotation. So the common center of mass is the new axis of rotation. So this is the center of rotation. So this distance is d1. So I have to take the entire mass, which is m1, times the distance 1 squared. So this is I1. I2 is a similar fashion. 1/2 times m2 r2 times its mass, which is m2, times its distance squared from the center of mass. So now, how much is r1? It's actually equal to 4 centimeters. The radius of the smaller of the two. How much is d1? It's equal to 6 centimeters. We just computed it. Okay? And how much is r2? That is actually 6 centimeters, the radius of the bigger of the two. So this radius is 6 centimeters. Okay? How far is the second one? It happened to be 4 centimeters. I don't know what this means in here. Dismiss. 4 centimeters. So these numbers, they look like symmetrical, but don't read too much into the symmetry at all. It just happened by design of this problem, okay? So it's not always true that these numbers will be like that. I mean, case in point, if I have, instead of 120 grams, let's say, for example, I have 800 grams or 1,000 grams. Obviously, these numbers will be completely, because the center of mass of this, any bigger, is going to be very close from this one instead, okay? So it's not, don't read too much into this kind of symmetry in the numbers, okay? So anyway, so we have I1, we have I2, we add them together, and we have I, and hopefully you guys can finish these numbers, okay? This is not a point particle. This is a disk. 1/2 mass times r squared. That's the moment of inertia of a disk. So this is, the 1/2 is coming from the fact that this is a disk. Both of them are disks, actually, including this 1/2 too. And then mass times this, and this is coming from the parallel axis theorem, and we're in business. So hopefully this fixes this problem. Once you find, of course, the I, you're going to plug it into this expression, and you're going to find omega f. Okay, this is one problem. Problem 2, okay? It gave you the mass of a, so let me draw the problem 2. I mean, problem 30, that is, in the book, of course. So you have a door that can pivot around this axis, and its width is 1 meter. And you have a bullet traveling in here with a velocity of 1,000 meters per second, 1 kilometer per second. Its mass is given to be 5 times 10 to the negative 3 kilogram, 5 gram bullet, that is. and the door has a mass that is equal to 18 kilogram, 18 kilogram, about 36 pounds. Okay, and it strikes at 10 centimeters from this point in here, and the length of this door is 1 meter. And of course, there was a bunch of questions in this problem in here. What else do I need? Okay, that's all we need. Then it says, gave us, first of all, it's asking, do we have an angular momentum for the before they collide? And they said that this bullet embeds itself in the door, so that this is an inelastic collision. Again, it's a perfectly inelastic collision. So the first one is, do we have an angular momentum? And if it is, how much it is? So those are two questions, A and B. Yes, we do. It's similar to the first problem anyway. So again, if I'm interested in to find the bullet, let's say, for example, it's far away here, okay? And I want to find its L, it's given by R cross P. Similar to the first fashion, the value of L is RP times sine of theta. This is the theta, basically, that I'm interested in. This is the R. The R is a hypotenuse in this right angle triangle. I'm going to try to draw a perfect line, so this is basically how much it is. So this is your R, and this is theta, and this is your distance, which is 90 centimeters, by the way, 0.9 meters, because the whole thing is 1 meter, and you deduct from it 10 centimeters, so you're left with 90 centimeters. So R times sine theta is the opposite to theta, which is 0.9. Okay, so that's the same thing as before. So the angular momentum before, with respect to the pivot point and axis passing by the pivot point, is going to be equal to 0.9 times the mass of the bullet, which is 10 to the negative 3, times the mass, times the, that's in kilogram, of course, times its speed, which is 10 to the power 3. So the whole thing is 0.9 kilogram meter squared per second. So this is easy to find that. So that's how much angular momentum we had. And okay, is the energy conserved? Absolutely not. It's not conserved, because actually this is an inelastic collision. As a matter of fact, they were very specific in stating the fact that you need to answer this question without doing any calculation. Well, since the bullet embedded itself in the door, then in this case, it's not it's a perfectly inelastic collision, and in the inelastic collision, the energy is not conserved. Therefore, the kinetic energy is not, so we can't really, that's the answer to that. Now, question number, and there is no potential, by the way, in this case at all, because of the fact that the door is swinging on the same plane, on the same level. It's not going up and down. So I'm in the picture here. This is from the top view, of course, okay? So this is the top view of the door. So it's not gaining or losing any potential energy. So the question was about the total energy. And as far as we're concerned, that's the only thing that is in question here, which is the kinetic energy. Since the kinetic energy is not conserved, therefore the total energy is not conserved. So that's answer C. Part D, so to find omega F, again, we're going to use the same thing as problem 26. We're going to use the conservation of angular momentum. So angular momentum before was 0.9 kilogram meter squared per second. That's going to be the same value actually afterwards. So at the end, L after, about the same pivot point, is going to be equal to I of the door plus the moment of inertia of the point bullet, which I'm going to treat it as a point particle. This is fully justified as being, I'm going to write a different symbol in here for this distance, because this whole thing is the symbol L. I'm going to call this L, the 90 centimeter, basically. We'll give it a name, which is little d, that's all, okay? So when it embeds itself, it's going to embed a distance, little d, which is 90 centimeters. And so its moment of inertia is going to be md squared, because it's a point particle. This is a point particle. I mean, a 5 gram bullet versus an 18 kilogram door, you can treat the 5 gram as a point particle. Now, the door from the top just looks like a rod when you look at it, and its moment of inertia with respect to the pivot point, which is one of its edges, it's 1/2 of its mass of the door times its length squared. This we saw, this is one of the first things we derived in class for the angular momentum, for the moment of inertia of a rod. So we have the I after, all we have to do is multiply it by omega final. This must be equal to 0.9, the value before. Okay, so we can find omega f, the omega with which the whole door swings, including that one. So it's going to be 0.9 divided by 1/3 the mass of the door, which is 18. Its length is 1 meter squared, that is, plus the mass of the bullet, which is 5 times 10 to the negative 3. Did I forget a 5 in there? I think I did. The mass is not 10 to the negative, 5 times 10 to the negative. So 5 times 0.9, the answer is not 0.9. 0.9, so it's 4.5 kilogram meter squared per second. By the way, you are responsible for these numbers, okay? I'm just helping you in here, trying to get you to understand the ideas. So this is 4.5 and not 0.9. So again, this is 4.5, okay? And then of course times the distance squared, okay? Obviously 18 divided by 3 is 6. So 4.5 divided by 6 plus this number, which is going to be a tiny number, okay? 0.9 squared, that's 0.81 times 5. What is it? 4.05. But don't forget it's 10 to the negative 3. So it's going to be 0.00405. So in other words, the answer is 4.5 divided by basically 6, okay? Again, check the numbers. That's your job, okay? Make sure you, and if there is a mistake, please let me know, at least in the ideas, okay? At this point, it's your job to check it, which is, what, 4/5, which is slightly more than 0.67 radians per second, okay? So that's it, your omega f. Then, of course, there is another part to this question. Find the energy of the system after, and is it bigger or less, okay? So let's find the energy after. So EI, obviously it's not going to be the same. EI was equal to 1/2 the mass of the bullet times its velocity squared. So 1/2 times 5 times 10 to the negative 3 times the velocity squared is 10 to the power 3 squared, that's 10 to the power 6. So 1/2 of 5 is 2.5 times 10 to the power 3. In other words, this is 2.5 kilojoules. So it's a bunch of energy, 2,500 joules, that is. How much is the energy afterwards? It's 1/2 E final, 1/2 of I of the door plus the mass of the bullet T squared times the omega F squared. Okay. Let's see here, we can do it. The I of the door is 1/3 the mass of the door. So first of all, we have 1/2 times the 1/3 of the door, mass of the door, which is 18 times its length squared, which is 1 meter squared, plus the mass of the bullet, which is 5 times 10 to the negative 3, times 0.9 squared. The whole thing times this number, I'm going to approximate it to 0.67. Okay, you guys are going to do it more accurately, okay? So 1/3 times 18, that's 6. 6 plus this tiny number, which is still a tiny number. So it's roughly 1/3 of a 6, 1/2 of a 6, plus some change in here, and some change, times 0.67. 1/2 of a 6, that's 3. So it's a 3 times roughly 0.67 squared, that is. 0.67 squared, okay? Okay, I'm gonna just see if I can get GeoGebra going for me quickly. My point in here is I need some number in here just to see how big that is, because it's going to be a very tiny number. A lot of energy is lost because it's an inelastic collision. So how much did we say? I'm not going to be, even in GeoGebra, I'm not going to spend time in here trying to get this thing. So we have 3 times 0.67 squared. Okay. It's about 1.5 joules, okay? It may be slightly more, slightly less, depending. So the point being in here is, you start with 2500 joules, then you end up with only 1.5 joules. A lot of it, of course, went to the deforming the wall by the bullet. The bullet itself probably is deformed. The wall is deformed in order to embed itself in it. And maybe also the noise and maybe also the heat and the smoke and all kinds of energy was lost in the process. So again, this is this problem. I think there is another part to it. I'm not sure exactly. I think, yeah, it says to take the wall and hang it upside down, basically. It's like pivoting like this. So when you hit it with the bullets, it's going to go up. And the question is how high it can go. Then in this case, you take the initial energy and this energy, not the whole energy, okay? Because part of the energy is lost. So once you find that, then you're going to find this energy, okay? So there is no conservation of energy. You can't say that it's 2500 joules, the entire energy is going to be converted into mgh. So it's going to be just the 1.5 joules converted into the mass of the bullet and the mass of the door times g times the height. From here, you can find how high the wall is. It's going to budge. It's not going to move much, honestly, because of the fact that the mass of the door is 38. How much was it? Was it 38 or 18 kilograms? Plus a tiny fraction, which is 0.5, so it's still 18, times g, which is 10, times h. This whole thing is about 1.5. Obviously, h is going to be 1.5 divided by 18 times, that's 180. So it's going to be fraction of a millimeter, probably, what, maybe half, not even a centimeter, okay? So the whole door, you take it upside down. Now we're looking at its side view. We're not looking at it from the top at all, okay? And you hit it with a bullet, it's going to swing. And how high it's going to climb? It's going to climb this much. It's center of mass anyway. The center of mass is the one that's going to climb. Any point in it, because it's a rigid body, will climb that much. So it's going to go... Sorry, that's the center of mass. We have to be careful in here, okay? Because it depends on that angle. Okay, so the center of mass will climb by practically nothing. What is it? 1/200, which is half a millimeter. Half a centimeter, I should say. Okay, so it's not even a centimeter complete. So that's the second part. And it was a what if part, so it was not really part of the question. It was what if. So it's not going to be much at all, because of the fact that it's this energy that is converted, not the entire 2500 joules. This energy, there is some, this is the initial energy of the system, of the bullet itself. When it lodges itself in the door, it's going to be ending up with this much energy, which is a tiny fraction of what it started from. And so that one is the one that is going to push the door higher. If you, instead of having a normal door like this, you have it hanging like this. The pivot points are on the top. It's like, I don't know what kind of door is that. It's like cat's doors, basically, or pet's doors when you put the cat so that the cat can come in and out. So if you hit it with a bullet, obviously this is not that door for the cat, because the door of the cat is not 18 kilograms. So big door like this one with a bullet that is 5 grams, although it's traveling supersonic because it's traveling by almost 3 times the speed of sound, but it's still not going to cause a lot of swinging for this door, because there is a lot of collision in here, a lot of heat in here, okay? So hopefully this is useful. If not, please reach out. Thank you.